This time, we are going to solve for the kernel and the nullity of these two different matrices under the linear transformation. Before we proceed with the appropriate steps, it's very important for us to examine the type of linear transformation here defined by these matrices so that we could determine the picture of the vectors that we are going to manipulate, since the kernel talks about a set of vectors, and also the zero vector that we are going to use. Take note here, this is a 3 by 2 matrix, same as here, 3 by 2 matrix. So following the pattern for m by n, so you have m by n, m is 3 and n is 2. Why do we need that? Because the linear transformation defined by a matrix is in this form, Rn to Rm. Since our n is 2, so we have R2 to R3. What's the purpose of this? The purpose for this is actually declaring the type of vector or that we are going to solve for, and the zero vector, because we will be using this. Okay, this process, the transformation of vector, the transformation of vector v is equal to a, the product of a and the same vector v, which is equal to the zero vector, and that's the goal for our kernel. We're going to solve for all possible values of this vector v that will satisfy the product of the matrix A times that said vector into a zero vector here. The zero vector here is not just any zero vector. It is an element of R3. Therefore, our zero vector here is 0, 0, and 0. And our vector v as element of R2 is example of this vector has components v sub 1 and v sub 2. It's very important for you to really structure this, because some of you might say it's a zero vector is just R2 or vector is until R3. So it's very important for you to structure that. And of course, you could see it better here. As we start now the process here, we will just try to come up with the reduced row echelon form of this what they call this one, matrix. Okay, the reduced row echelon form. What we could do here is simply copy it first before applying this process. 1, 2, -1, -2, 1, and then 1. Let's make both of these zeros. So what we could do is to add row 1 to row 2 for a new row 2, and multiply -1 to row 1 plus row 3 to have 0 here in our row 3. This would mean this is still 1 and 2. So we add this 2, we have 0, add this 0 as well. So you have -1 times 1 is -1 plus this, we have 0. -1 times 2 is -2 plus this -1. Since we have a row here of zeros, let's interchange row 2 and row 3, because to make it is in a form of reduced row echelon form, all the rows with 0 entries must be at the bottommost part. So we have here 1, 2, 0, -1, and then we have here 0 and 0. And finally, let's make this +1. So you will have here negative of row 2 to become a new row 2. 1, 2, 0, 1, 0, and 0. This is not yet in reduced row echelon form, but actually we can continue this. This is already in a row echelon form. We can now use this and pair it with this idea. But just for the same pattern as the previous video, and you might want to check the previous video before this, we used there the reduced row echelon form. So let's make this 0 as well. So -2 on row 2 plus row 1. For a new row 1, we will come up with 1, 0, 0 here, 0, 1. -2 times 1 is -2 plus 2, 0. This is now in its reduced row echelon form. Okay? From here, let's now multiply the vector v and equate it to the zero vector. Again, the vector v is in R2, the zero vector is in R3. Okay? When you multiply this with v sub 1 and v sub 2, actually the product is now defined. This is also another hint that it's really in R2, because if, say for example, you're adding here v sub 3, you cannot multiply this anymore, and then the product is now not defined. And it's equal to the 0 vector 0, 0, 0 in R3. So we'll have this product. We have v sub 1 equal to 0, v sub 2 equal to 0. Notice that we will have an what you call this one, exact results, because our form is in reduced row echelon form, and these are now the components of your vector. So your vector here that will result this matrix into a zero matrix, I mean 0 vector, is the vector of 0, 0. So for our kernel of T, we have the set containing 0 and 0. I mean the set containing the vector 0, 0. Okay? Now, we have here this kernel. The nullity of T is the dimension of the basis of the kernel. We have one element on our kernel of T, which is again the 0 vector. But if that one element is a 0 vector itself, the nullity doesn't count the 0 vector. Hence, the nullity of T is 0. Not 1, but 0, because that's the dimension of the basis of the kernel. These are nullity of T and kernel of T for the first given matrix. Duplicating the process on the second, again, we will be using this idea and these ideas as well, because they are the same 3 by 2 matrices. So let's come up with the reduced row echelon form of this. 1, 1, negative 1, 2, 0, and 1. Let's make the 0. We will be adding row 1 and row 2 for a new row 2. This is already 0, so no need to manipulate that. 1, 1. So 1 plus negative 1 is 0. 1 plus 2 is 3. Then 0 and 1 here. What you could do here is, yes, you can divide this by, or multiply this by 1/3, row 2. For a new row 2, you have 1, 1, 0, 1, 0, and then 1 here. Then, finally, you can actually multiply negative 1 to R2, that's R2, plus R3 to have a new R3 to make this 0. And probably you can just combine the product of negative R2 to R1 to have a new R1. I'm just targeting at 1, so this will become 0 as well. Okay, so what happens here is this one here. So 1, 0, 0. So negative of R2 is 1 plus this, so that's 0. Same thing plus that 0 here as well. This is now our reduced row echelon form. Okay, multiplying it to our vector in R2 and equating it to 0 vector in R3. We'll have these forms. V sub 1 is still 0. V sub 2 is still 0. So with this, the vector that can make our matrix be equal to a 0 vector is the 0 vector itself. So same as earlier, the kernel is a set containing the 0 vector, and the nullity, since the element of the kernel of T is 0 vector itself, the nullity is 0. So we are done with the nullity and the kernel of T for these two given 3 by 2 matrices. So please review these processes. Thank you very much for watching.